Hello, this is the second video lecture on chapter 16, and in this video I will be talking about the three subjects that you see in front of you: sound waves, decibel level, and the Doppler effect. Okay, these are the remaining three topics that I want to talk about in chapter 16. I will begin with the sound wave. You may recall from previous lecture, we said that waves transport energy from one place to another, and as the wave travels through a medium, the energy is transferred as a vibrational energy from one particle to another, right? The important result is that energy transported by the wave is proportional to the square of the amplitude. We'll talk about that in a second. But what I'm going to talk about today is, or I want to start with, the concept of what is called intensity. Intensity of the wave. Now, you remember the word power. Let me just, and we talked about power. We know that power is energy over time. Okay? The intensity is power over area. Okay? This is a very important result. What that means is the following. Think of the word energy as the word loudness. When you say something loud, that means something that you can hear it clearly, or maybe it could it's so loud it hurt your ears. So loudness is a sensation. Okay? Intensity is a measure of that loudness. Okay? Remember, the word loudness is more of a subjective concept. Subjective. Intensity is objective. You know what I mean? Difference between subjective and objective in philosophy or in objective in philosophy or science. When I say something subjective, it's something that is depends on how you perceive it. For example, you may say, I like apple pie, but I don't like, say, blackberry pie. That's subjective. It's just a matter of taste, okay? The word hate and love are both subjective concepts. However, when you say something like 7 is a prime number, that's an objective statement. And no one will disagree on that. Nobody's going to argue and say, I disagree with you, okay? So when you say something loud, again, that's a subjective thing. You know, what appears to be loud for you may not be loud for me, and so on. But intensity, which is in a way, it is a measure of loudness. Okay, it's the measure of the volume of the sound. It is an objective concept, and it is equal to the power divided by the area. Let me explain. Let's say, for example, there is a sound source. Okay, and the sound source, the loudness of it or the intensity of it is measured, again, I am using the wrong word. The power of the source, which is, think of it like the loudness, okay? So the power of the source, think of it like, I'm going to quote it, loudness, okay? For example, a siren, okay? That's very loud, right? So it has a great power. You got that? However, it depends, the intensity of the siren depends on how far are you from it. You get that? So the power is there, you know, so the output power, you know, the energy coming out of the siren is, say, large energy, but it depends on the intensity of it, or the loudness of it rather. It depends on how far are you from it. And that's why we have this formula right here. So it depends on the power over area. Now, why do we use area rather than, say, distance? Well, here is how it works. Let's say, for example, here is let me draw, say, XYZ coordinate like this, and assume that the power source is right here. Say a siren or whatever, any sound source. Okay. The way the wave travels, it doesn't really travel in a ray. It travels as a sphere. Think of it like a sphere. Let's say when I say the word check, okay? When I say this word, think of it like there is a sphere or a spherical wavefront, we call it, and this sphere is swelling. Oops, I can't draw it as a parallel to it. Is swelling and getting bigger and bigger away from it like that. I'm trying my best to draw it. Okay, and it's traveling radially like this at the speed of the wave. Let's say the sound. Okay, so if it's a sound wave, so a speed traveling at the speed of sound, which is roughly 335 or something like that meter per second. If it is a light source, so it's traveling at the speed of light, and so on. Okay, so you get this sphere that is traveling, and then let's say you have an observer here. I'm going to symbolize the observer with an ear. Okay, and so the observer is a distance r away from the source. Remember, this is the source right here, the dot right at the center of the origin of the coordinate, and this is the radius. Okay, by the time the sound reaches the observer's ear, so it basically what reaches is really that spherical wavefront. A sphere reaches him or her, whatever. So this sphere, there it is. Okay, it has a radius r. Okay, and the surface area of this sphere, shall I call it A, for example, is equal to 4 pi r squared. Okay, so we measure the area here, the one you see in the equation right there. This area is really the surface area of the spherical wave. You got that? So when we measure intensity, I for intensity is equal to the power P over the area A. Again, this area is the surface area of a sphere. Okay, so that's equal to the power over 4 pi r squared. Got it so far? Okay. Now, let's assume there are two observers. Here is the first observer. I'm going to call him observer 1. And of course, he is at an r1 away from the source, right? And let's assume we have another observer. Let's put him here. Nice looking here. And he is at a distance r2, observer 2, okay? At a distance r2 away. And of course, he's going to receive a spherical wave right there. Okay, that's spherical wave. With a different radius. So that means, so this is, let's say this is I1. This is the intensity measured by observer 1. So he's going to say the intensity of the wave is equal to power over 4 pi r1 squared. Observer 2, however, is going to measure a different intensity, power over 4 pi r2 squared. Obviously, the intensity I1 is greater in number, right? Is greater. Okay. So how are the two relations related to each other? Well, let's solve for P, the power. Now, the power of the source is the same for both of them, correct? So the power in the first equation would be 4 pi r1 squared I1. And then the power for the other one here is 4 pi r2 squared I2. Of course, those two equations must be equal. Let me equate them. So I have 4 pi r1 squared I1 equals 4 pi r2 squared I2. And then the pi 4 cancel out. I end up with an interesting relationship. I over 2 over I sub 2 over I sub 1 equals to I r1 squared over r2 squared. Okay? Make sure you write this equation and box it, because we're going to be using it. It's a very important equation. I'll give an example and show you how this works. Let's say, for example, if the distance is doubled, how the intensity will change. Okay? So for example, I have, just like this diagram that I showed here. So let's say that this is R1, okay? So this observer is hearing some I1, intensity 1, in relation to the source here. And let's assume R2 is equal to 2R1. So how would I2 relate to I1. You got that? Simple. So I can just use this relationship. So we know that R2 is equal to 2R1. So I can use this relationship here. So therefore, I2 over I1 is equal to R1 over R2 quantity squared. I like to write it this way rather than squared. I'll just put it like that. And then I'm going to plug it in. So I have here R1 over 2R1 squared. So that will be 1 over 4. So in other words, I2 is equal to 1/4 of I1. You got that? So it drops by 1/4 if the distance is doubled, and so on. You got it? I'll give you more examples in a minute. Okay, well, here's one more example. Since I'm using my notes, I'm not using your book to do this lecture. Your book doesn't cover it very well. Here's another example. The title of the example, earthquake intensity. Earthquake intensity. Okay, it says that the intensity of an earthquake traveling through the earth and detected 100 kilometers from the source is 10 to the 6 watt per meter squared. Question: what is the intensity of the wave detected 400 kilometers? Okay, I forgot to mention something before I do this problem. Let me go back to the formula, the equation that describes intensity, which is right here. Okay, so we said that intensity is equal to power over area. So therefore, the unit here, the unit of intensity is what? Watt per meter squared. You got that? So it is watt per meter squared. This is very important. I forgot to mention that. Okay, that's the unit of intensity, watt per meter squared. Later on, we're going to use decibel for that, to convert this unit to decibel. Okay, but that's what it is right now. Okay, watt per meter squared. Okay, back to our equation, to our example. So simple formula. So I can just use the same equation that I have just displayed. I2 over I1 equals R1 over R2 quantity squared. Okay, hold on, I got this mastering wants me to keep me signed in. Okay, and of course, if I assume that it's detected 100 kilometers, let's make that R1. I'm going to keep the kilometer because they're going to cancel out with the 400 kilometers. And R2 is 400 kilometer. And then he tells me that for R1, the intensity is 10 to the 6 watt per meter squared. I can simply just plug it in. It's a pretty simple problem, right? So I have here, he's asking for I2. So I2 over I1 is equal to, R1 is 100 over 400 quantity squared. The kilometers cancel out, right? The zeros cancel out as well. So you end up with 1 over 16. And therefore, the intensity I2 is 1 over 16 times I1, which is 1 over 16 times 10 to the 6. 1 over 16 is equal to, let me use my calculator. 1 divided by 1/6 equals 0.0625 times 10 to the 6. So therefore, the intensity I2 is equal to 6.25 0.25 times 10 to the 4th watt per meter squared. As you can see, it drops, right? Because it is 4 times larger, you know, the distance from 100 to 400, and then so it drops. You got it? Okay. That's basically what intensity is. Now, let's talk about sound as a wave. Now, the speed of sound in general, the speed of sound, I think we're going to call it, I'm just going to call it V for now. Because when I cover a Doppler effect, it's a different symbol. Anyway, so the speed of sound in air is around, let me just put it, roughly around 331 meter per second, okay, in air. That's the average speed of sound, 330, maybe we can just say 330, okay? There is a simple formula that will help you determine what's the speed of sound in various material, okay? And the formula says 331 plus 0.6 T. I'm not sure if it's in the book, this formula. I just have it in my notes. Where T here is the temperature. So the speed of sound depends on temperature. And the speed equal 331 meter per second. This is a speed of sound at STP. You know, the standard temperature and pressure at the temperature of 0 degrees Celsius, and the pressure is 1 atm, okay? So that's what it is, 331. Now, let's say you want to know what the speed of sound at a different temperature, say at room temperature, where the temperature is about 20 degrees Celsius. All you need to do, you put the temperature here for the T, and remember this T is not in Kelvin, okay? You simply put it in Celsius. You got that? So the people who study waves and stuff, they don't think about Kelvin, only people of thermodynamics. So basically V equals 331 plus 0.6 multiplied by 20 degrees Celsius. You got that? And then when you calculate that, 331 plus 0.6, 0.6 times 20, answer 12. So that will be 12 here, and that will be equal to roughly 343 meter per second. You got it? Okay. All right. Now we come to decibels. This chapter, I hope you are finding it easy, definitely easier than the thermodynamic chapters, and more interesting maybe. Okay, decibels. When we say decibels, we're basically talking about, we're trying to find a way to measure the loudness or the intensity of sound, of the sound that we hear in our human ear. You get that? We go back to, well, here is what we know about the human ear. The human ear has a huge range of frequencies, okay, or intensities. The human ear can detect intensity as low as 10 to the negative 12 watt per meter squared. Okay, this is extremely low. This number, this magic number, we call it the threshold of hearing. The threshold of hearing. Okay, which is the what's opposite of loud? The quietest, or the lowest sound the human ear could hear. I'm sure the dog would hear it easily, and below that. But that's called the threshold of hearing for the human ear, remember, okay? So this is kind of a subjective statement, if you will. And then you have, so we said that we can detect as low as that, and it also can detect as high as up to 1 watt per meter squared. Of course, we can detect even larger than that, but it would basically break your eardrum, or it would be extremely large. So we call this number the threshold of pain. Okay, so those are the two ranges. So here so we have a very wide range, in the magnitude of 10 to the 12, as you can see, from 10 to the negative 12 to 1. That's a magnitude of 10 to the 12. Okay. So a scientist by the name Alexander Graham Bell, I believe in the 19th century, I'm not sure, he came up with a unit. It's called the Bell. I believe it's after his name, Bell. B-E-L. And look at it's a small letters, all of them, okay? It's a bell, okay? And this bell, this unit, is later on, it was developed into decibel, deci for 10, okay? Decibel, where deci means 10, if you remember, right? So 10 decibels, and the unit of it is small letter D, capital letter B, okay? This is this is how it looks like, okay? Small letter D, capital letter B is equal to 1 bell, okay? Now, let me go back to this number here, 10 to the negative 12, the threshold of hearing. There's a symbol, the mathematical symbol for it is I naught, okay? So when we see that, this is our symbol. I naught means the threshold of hearing, okay? So I naught is 10 to the negative 12 watt per meter squared. The sound level, so what he did after he developed these, he developed a logarithmic formula that allows us to calculate the loudness of sound, and it is known as the sound level. So when you hear the term sound level, we are really looking at the decibel level, okay? Sound level. And the formula goes like this. Beta is equal to 10 times logarithm of I, the intensity, over I naught. And the unit of this formula will be automatically in the decibel level. Okay, let me give you some examples and show you what that means. Remember, I naught here is what? The threshold of hearing, which is 10 to the negative 12, okay? Let me give an example. So let me just say, such that I naught is equal to 1 times 10 to the negative 12 watt per meter squared. Okay. Here's an example. What is the sound level whose intensity is I equals 10 to the negative 10 watt per meter squared? Okay? We want to know. So we say decibel, what is the sound level? It means he's looking for the decibel, beta. Okay? So we say beta is equal to 10 times logarithm of I, which is 10 to the negative 10, divided by 10 to the negative 12. See how easy it is? You just plug it in. So we have 10 log, what? 10 to the, what is that? 10 to the 100, 10 to the 2, which is 100, right? Do you agree with me on that? And what is that equal to? Remember, log 10 is 1, right? So when I put the 2 over there, so it becomes 200 log 10. I'm doing it in detail, so that will be 200. I'm sorry, that's 2 times 10. This is, sorry, that's a 20. So 20, remember, this is log 1, log 10 is 1. So that's 20 decibel. Here's the question. Is this loud or not loud? 120. Well, let me show you a table. This is interesting. There is a table here in the book. There they are. Let's see if I can magnify it a little bit. There we go. Okay. Just to give you a feel for those numbers. Look at that. So here we have a threshold of hearing is 0. Why is 0? Well, I will come back to it. A person breathing at 3 meters. So let's say they are observing a person. You can hear him or her breathing. The decibel level is 10. Okay. A whisper 1 meter away, which is about 3 feet away, is 20. Okay. So this number is about the sound level of a whisper. Or, see what I'm saying? Okay. Quiet room, 30. Outdoors, no traffic, 40. Quiet restaurant, quiet, maybe just people chattering very quietly and so on, 50. Normal conversation at 1 meter, so somebody's talking to you, it's about 60. Busy traffic, 70. Vacuum cleaner, which is usually loud, that's 80. Okay, for a user. Okay, so the user is really close to the vacuum cleaner. Maybe he is about, he or she about 1.5 meters away from the engine, from the motor. Niagara Falls, if you've ever been there, it's 90. It is pretty loud. Snowblower at 2 meters away, that's really loud. 100. Stereo, maximum volume. When you crank it up really loud in the car or something, 110. And then you get the threshold of pain, which is 120. 120 is the threshold of pain, by the way. I'll show it to you in a sec. Okay, so a rock concert is 120. As a matter of fact, I know that in rock concerts, there is a law where they cannot have a decibel level larger than 120 because that's the threshold of pain. It's just too painful for a human ear. And then you get the threshold of pain. My understanding, threshold of pain is 120. Our book is 130. Loudest football stadium, I don't even know what that means, but it's 140. Oh, okay, so I guess maybe the spectators, the audience. But let me go. There is another, my understanding, the threshold of pain is 120, not 130. I'm surprised by this result. Here's a table that I got just from the internet. Loudest possible rock concert. Again, he's a little bit different here. Let's see, breathing is 10, whisper is 20, library is 30. Quiet office, 50. Conversation, 60. Piano practice, 65. Noisy restaurant, 70. Alarm clock, 75. Vacuum cleaner, 80. Garbage disposal, 85, and so on. What is the threshold of pain? Loudest possible sound is 190. I guess larger than that, you explode, your ear explode. Just begin to vibrate, 150. Rock concert, 140. Again, it is 120. I've seen it several times, 120, not 140, and so on. Okay. Okay. Let me go back to the notes here. So this 120 here basically is a whisper, roughly, or something like that. Again, maybe we can argue and say that the reason he's saying the threshold of pain is 130, because this is a subjective statement. You see what I'm saying? I can show you, I have another book, and it said the threshold of pain is 120. So I guess it depends on how you see it, okay? Maybe that would be one way to see it. But let's see if we can prove it together. Remember we said that the threshold of hearing is 10 to the negative 12, and the threshold of pain is 1 watt. I know these are agreed upon. So let's calculate that in terms of sound level. So for I naught is equal to 10 to the negative 12, right? So in this case, beta is equal to 10 log 10 to the negative 12 over 10 to the negative 12. So that will be 10 log, is that right? Did I do it right? 10 to the negative 12 or 10 to the negative 12, that'll be 1 here. And of course, log 1 is what is 0, correct? So that will be 0. See what I'm saying? Now, let's say the threshold of pain is 1 watt per meter squared. Is that right? So beta is equal to 10 log 1 over 10 to the negative 12. So that makes it 10 times log 10 to the 12. So that will be 10 times 12 times log 10, which is 1. And that's 120, see? I guess the book is wrong then. So there we go. This is the threshold of pain, 120, not 130. But anyway. Got it, guys? Okay, let me give you another example. I have like 2-3 examples of that. Let me just go through this one. Here we have a loudspeaker. So we have a speaker produces frequencies You know what? I don't want to do this problem. It's a little bit not related to what we're doing. I want to do the next one. Sorry about that. It's the reason it's just too simple. It's very similar to the problem that we have just done. I want to do this one. This one is kind of interesting. We have a sound level. Okay, the title is Airplane Roar. Airplane Roar. So we have a sound level measured at 30 meter for a plane, okay, to be 140 decibels, okay? Here's the question. What is the sound level at 300 meters? Okay? So how do we do it? All right, you can pause the video, try to do it yourself, and then come back and we'll do it. So since we're not live, so I have to start working on it immediately. So the first thing I want to do is I want to find, from the first statement here, I want to find the corresponding I, the corresponding intensity for this one. I'm going to call that intensity 1 instead of saying. And then for that, for this case, I'm going to call that intensity 2. So let me find I1 first, okay? So we're going to call that beta 1 is equal to 10 log I1 over I0. Is that okay? And then I can solve for it. So I beta 1, this is beta 1 right here, and that's equal to 140. Is that right? So move the 10 to the other side, so it becomes log I1 over I0 is equal to 14. And then raise everything to the power of to the base 10, so it becomes 10 to the 14 equals I1 over I0. I am assuming all of you are very good in logarithms, okay? So I'm not going to give you an algebra class on how to do logarithms. I'm assuming that you know how to do that. So in this case, we'll have I1 is equal to I0 times 10 to the 14. Of course, I0 is 10 to the negative 12 times 10 to the 14. And that will give us 10 to the second, which is 100 watt per meter squared. There we go. So the intensity here is 100 watt per meter squared. Okay, guys? Now this one is what? At R1 equals 30 meters as given by the problem. So far, so good? Okay. Now, I can use the first formula that we dealt with, this one. We said that I1 over I2 is equal to R2 over R1 quantity squared to find I2. Okay? So plug it in. So I1 is 100 over I2 equals R2 is 300 over 30 quantity squared. And so therefore, I2, if you do the math here, it's pretty easy, you'll end up with 1 watt per meter squared. There we go. I found I2. Now he said, what is the decibel level, or the sound level? I like to call it decibel level. What's the decibel level, the sound level? So I just go back and say beta 2 is equal to 10 log I2 over I naught, and you just plug it in, right? So you have 10 log I2 is 1 over 10 to the negative 12, and that will give me 10 times 12, and that'll be 120 decibel. And there we go, that's the answer. You got it, guys? Okay. Here's a question for you. I'm not going to do it. I'm just going to give it to you as, homework. You don't need to submit it or anything. He says, show that the difference in decibel level, which is sound level, beta 1 and beta 2 is related to the ratio of R1 and R2 by the following relation. Beta 2 minus beta 1 equals 20 log R1 over R2. Okay, it's a simple problem, but it's actually the previous problem here is related to it. In other words, I can use this formula to get this answer immediately. Okay, just plug it in, and you will get the answer immediately. You want me to show you? Sure, here. That's basically what the question is. I'm not going to solve it for you. You should be able to do it, in a couple of steps. But let's see if this actually works. Try it for previous example. How do I do that? Well, what we are given the distance R1 and R2. See what I'm saying? We are given that distance, and so we can say that beta 2 minus beta 1 is equal to 20 log 30 over 300. Is that right? So that'll be 20 log, what is that? 30 over 300. Let me use my calculator. 30 divided by 300, 10 to the negative 1. It's basically 0.1, right? 10 to the negative 1, so that will be negative 20. So that's beta 2 minus beta 1. Now you can finish this problem if you want to. I am not going to go any further. But let's look at beta 2 and beta 1 and see if the difference between them is negative 20. Is that true? So look at that. Beta 2 is 120, and beta 1 is, what is beta 1? Is 100? I'm sorry, beta 1 is 140 right there, right? So if you take the difference between them, indeed, it is equal to negative 20, right? And then how would you get, so therefore, beta, I'm looking for beta 2, right? So beta 2 is equal to negative 20 plus beta 1. So that's minus 20 plus 140, and that's equal to 120 decibel. See how fast I could do it with this little identity here? But I wanted to prove it. If you can't prove it, if you have any difficulty, please post it in the discussion forum or ask the professor, and I will be more than happy to show you how to do that. Again, I'm looking at how I did it. I'm looking at it's actually 1, 2, 3 steps. It's really easy. Okay. Hope you'll be able to do it. All right, one more problem on decibel, and then we'll move to Doppler. This one is kind of interesting, this problem. I got it from another book as well. It says you have a noisy machine in a factory. Okay? Produces 80 decibels. Okay? Here is a question. This is interesting. How many identical machines could you add to the factory without exceeding 90 decibels? Is that interesting? I mean, that's actually probably a realistic problem. You know, you are an engineer working in a factory, and the factory has a particular machine that produces 80. But, you know, the people of the factory, they need more than this machine. They need as many as possible. But because of regulation, federal regulation or whatever, the factory cannot exceed 90 decibels. Remember, 90 decibels is probably too big. What's a 90 decibel? Let's get a feel for that 90 decibel. Let me go back to that table. What's 90? Is roughly tractor, subway, garbage disposal, busy hotel lobby. So anyway, blender. So somewhere between the sound of a blender and a garbage disposal, okay? So that would be the loudness. Of course, it may sound not very loud, but imagine if you're working there 8 hours a day, 9 hours a day, and you're constantly hearing that garbage disposal for 8 hours continuously. That's going to hurt your ear. So you want it to be a little bit lower, or you don't want it to exceed that, for example. So that's basically what he's saying. So how many identical machines? Okay, you will learn that from this example is that it's not additive. It's not like if I have a machine that produces 80 decibel, if I bring another machine, it's going to be 80 plus 80, 160. That doesn't work that way. I mean, remember the threshold of pain is 120. So if you have two machines, each of them produces 80. So the addition here is 160. That's just going to blow up your eardrum. But that's not true. Okay, it's not additive in that sense. Okay, let me show you how it works. Very interesting. So we have beta is equal to 10. Remember, this is a logarithmic scale, so it's not additive in that sense. Is equal to log. Oh, I forgot to mention. However, intensities can be added up. You can add up intensity. So if I have beta equals to I over I naught, well, how many machines? How many identical machines? Let me call them n. So it's going to be n times the intensity. You see that? That's the trick. Once you get that, that's it. You're done with the problem. And this equal to 90 decibel. And all you need to do, 90 decibel. All you need to do now is you just solve for n. How many machines you can add. You see what I'm saying? So this case becomes log ni over I naught is equal to 9. And so that will be ni over I naught equals 10 to the power of 9. And so ni is equal to 10 to the power of 9 times 10 to the negative 12. Is that right? So that's 10 to the negative 3 ni. Therefore, I is equal to, n. N is equal to 10 to the negative 3 over I. Correct? All right, so now I need to find I. So what is I? What is I? Well, he says I have the decibel level is 80 decibel. So what correspond to what intensity correspond to 80? So let me go back. So after I did this, so now I go back and say beta is equal to 10 log I over I naught. And of course, this beta is equal to 80. You see what I'm saying? So now I need to find I. You see what I'm saying? So when I do that, so it becomes log I over I naught. I should have done this first before this one. But anyway, it doesn't matter. So I have here 8. And then, so that will be I is I'm going to do it in one step. I naught times 8. Times 10 to the 8, sorry. And this will give me 10 to the negative 12 times 10 to the 8. So I in this case is equal to 10 to the negative 4, right? Watt per meter squared. Okay. Now I go back and take this and plug it right here. okay? So when I plug it in, so therefore n is equal to 10 to the negative 3 over 10 to the negative 4, and that gives me 10 to the negative 3 times 10 to the 4th, so that'll be 10. So therefore, I can add up to 10 machines. You see what I'm saying? Isn't that interesting? It's I like this problem. When I first read it and solved it, I was kind of impressed with it. I didn't know, it gives you the impression that it's additive, but it's not. Okay, so you can add up to 10 machines to get only 10 decibel difference. Okay, good. All right, that's basically the topics that I want to talk about in terms of decibel level. The last topic I want to talk about is the Doppler effect. This is a very easy topic. I hope it is for a lot of you. I'm going to go over it very quickly. And it basically, you just need to learn which formula to use for the Doppler effect. So first of all, what is the Doppler effect? The Doppler effect is used a lot in our daily lives. For example, astronomers use it to measure how fast, say, a star is receding from us, or a galaxy, or when they look for those planets, for those exoplanets, they use the Doppler effect to see how fast the star is moving around the star, how fast the planet is moving around its own parent star, and so on. The people of weather, they use it to measure the speed of clouds or wind and so on. And then in physics, we also use it, and we're just going to apply it to simple things, and that is how sound, how we perceive sound in terms of Doppler effect. Here is how it works. I'm sure you have observed this before. Let's say you are standing beside the street, and let's say the street is empty, there are no traffic there, and then you hear a car coming, okay, just one car. And from the way the sound of the car approaching you or coming closer to you is different from the way the car after it passes you. For example, you hear something like, right? It changes. It goes as it is approaching you. The sound is almost like high pitch, high frequency. As it passes you, it is lower pitch. Okay. Let me show you a diagram. Show you how that works. Let's say, for example, here is the street. Here is the car coming. Okay. The car is going with a speed v, okay, say 50 miles an hour or something. You are the observer, okay, you are the observer. Let's assume that you are here. That's the ear, right? And the car passes you. So here's the car passing you here. Same car. And it's still going at the same velocity v, okay? Now, as the car is moving towards you, the wheels are pounding the street, and you get the engine, and then you have the air drag, it's hitting the air and all that. So it's producing sound, okay? That's basically the sound of a car. So it's producing sound, and those sound waves, they are spherical in nature. They are moving in this direction as they approach you, okay? So that's the sound, the velocity of sound, okay? So you hear this velocity of the car, and this is the velocity of sound. So what you will receive here is the velocity of sound plus the velocity of the car. Okay, so if it's, for example, 340 plus 55 miles an hour, whatever it is, so that's what you are receiving. Okay. However, when the car receding from you here, well, here is the sound, the same spherical wave are coming towards you. But now, look at this. The speed of sound is opposite that of the speed of a car. So here, the speed of sound that is coming towards you is actually subtracted from the speed of a car. Okay? The difference between those two speeds is what gives you that, that Doppler effect, what is called the Doppler effect, is that this one, as it is coming this way, this is high pitch, and this is lower. Not necessarily low pitch, but it's lower pitch. The word pitch here means, of course, frequency. And that's what the Doppler effect is all about. We want to measure the frequency as the car approaches you, and we want to measure the frequency as the car is receding from you. You are the observer, O, okay? And the car is the source, S, okay? Remember those terms. These are the terms that I'm going to be using. So O for the observer, or big O, and S for the source of sound, okay? And that is a bunch of formulas, 1, 2, and 3 sets of formulas. I'm going to write them down first before we start doing problems. I'm sure you've seen those things before in your previous classes, but here they are. Okay, we have 3 cases here. Case number 1. Again, I'm just going to write them down. Please, as I write them down on your notepad, whatever. So here they are. So we have a source and an observer. Let's assume the source is at rest and the observer in motion. In other words, let's say, for example, you are driving your car downtown, okay, and you see a party going on. There is a band playing right there on the street, okay, as you drive. So the band is not moving. This is the source of sound. The source is the band playing, and you driving your car. So as you approach the band and then as you recede from the band, okay, so you are moving toward the source and away from the source, you'll have a different frequency. And the formula is this. The frequency received by you, we're going to call it F prime, which is the one that you are measuring after the Doppler effect, is equal to the actual frequency coming out of the band at rest, okay, and V plus minus VO over V. Now when you say V here is the speed of sound. And VO is the speed of the observer. Okay, so as you're moving with your car at 25 miles an hour or something, that's your speed, measured of course in meters per second. The frequency here is the frequency of the source, okay? Again, I'll come back to it. Now, I have plus or minus. What does that mean? It's plus if you are moving toward the sound, toward source. Minus if you are away, moving away from the source. Got it? I'll come back to this formula. I'll do an example. Let me do it again. Like I said, there are 3 formulas. Here's the first one. Second one. Now we have source in motion. Say, for example, a siren, an ambulance moving, and you are standing by the street and you see the sign, the fire truck is coming. And then the observer is at rest. And in this case, the frequency observed by you is the frequency of the source, the siren, for example, V over V minus plus Vs. S here, the velocity of the source, not sound. Okay, remember, V is the speed of sound. VO, observer, and Vs is source. Okay, got it? Okay, where here, the minus is the source is moving toward you. In other words, approaching you. And plus is moving away from O. Okay? The last equation, and then we'll do some problems, is that what if the sound, the source and the observer are in motion? For example, you're driving a car going north, and then a fire truck coming in the opposite direction. Okay, they both. So now you want to measure the speed of the frequency of the truck as it approaches you, or after it moves away from you or passes you. Okay, so here we have source in motion, and the observer is also in motion. In this case, we would have the following formula. Look how it looks. V plus minus VO. VO is the speed of the observer, divided by V minus plus. See the difference in the two? Plus minus, minus plus. Okay, Vs. S here is the speed of the source. Okay, so you pick the upper unit, the upper sign, when the source is, or the source and the observer are moving towards each other. Towards each other. Okay? They approach each other, that is. And then lower, and they're moving away. Got it? Okay, let's do a couple of problems and then we'll end this lecture. I have 1, 2, 3 problems. No, 2 actually. 2 problems. Okay. We're coming up to an hour. So we have here train moving away, I'm sorry, I read it wrong. I'll just say train moving with speed 40. This is 40. I'm sorry, my hand is getting tired. 40 meters per second. This is not the easiest pen to write with. Anyway, train moving with a speed of 40 meters per second sounds its whistle which has a frequency of 500 hertz. Okay, I mean, in other words, the engineer designed that whistle to produce 500 hertz. That would be the F here, though. This F that you see here. You got that? That's the actual frequency of the whistle or whatever the sound source. Okay. We have. He says determine the frequency heard by standing observer as the train approaches the observer, as the train approaches. Okay, simple. So what do you think is going to be, higher or lower as it is approaching? It should be higher, correct? As it approaches. This is part A actually. As train approach, that's A, and B as train move away. Okay, let's do part A. So as a train, okay, in this case, first of all, we have to classify this problem. What do we have here? We have the source in motion, correct? And then the observer at rest. So we're going to go back to those formulas and look for source in motion and observer at rest. So this is the formula we're going to be using, right? And it is approaching, so that's going to be, we're going to take the minus sign. You got it? So now it becomes, the formula becomes like this. F equals F prime, and you take the minus sign, V over V minus Vs, and then we just plug it in. So we have 500, 345. This is the speed of sound in my note. And by the way, each book has its own speed of sound. Let me just look at our book and see what's the speed of sound in our book. Because in mastering, if you use 345 and it's not 340, you're going to get the wrong answer. Each book got their own convention. Let me look it up. There we go. Okay, the speed of sound according to our book, let me write it down here, which is the one you want to use at mastering, is 343 meter per second. Got it? Use this one. Don't use 345. I'm going to use 345 because my note says that. Okay, that's the one we use. Okay, and I got it from example 1611, page 447, if this is important. And he has it right there. He said the velocity of sound is 343. Honestly, other books will say 341. You know, everybody got their own little convention. But anyway, so that's the one we're going to be using. So back to our problem. Divided by 345 minus the speed of the source is 40. And then we just plug it in and we end up with 566 hertz. So in other words, the frequency will be at a higher pitch, will be a higher frequency as the train approaches you. Now, if it moves away, okay, again, we use the same formula, except that it's a plus, correct? So it's going to be F equals F prime V over V plus Vs, and then we just plug it in. It's 500, 345 divided by 345 plus 40, and when you calculate that, it is 488 hertz. There we go. It's a lower pitch, actually lower than the actual frequency. I'm sorry, 1 second. Did I do something wrong with it? The prime does, oh, I don't like the, I'm sorry. I should have put the prime here. You're probably screaming at me now. This is, the prime is right there. Hope I didn't confuse anyone with that. There we go. Is that right? Okay. The last example that I want to do before I finish my lecture here is another one here. I have, it says noisy siren. So we have an ambulance travels down the road. Speed, I'm just going to be brief on it, 75 miles an hour, mph, okay? Siren of the ambulance emits sound of frequency f equals 400 hertz, okay? Now here's a question. What frequency is heard by a passenger in a car moving 55 miles per hour in opposite direction? Okay, A, as car approaches, okay, and B, as car move away, okay? All right, simple, huh? All you need to do, well, in this case, I have the source is in motion, and the observer is also in motion. So I'm going to use the third equation. Here it is right there. This one right here. Use red. Got that. This one here. Okay? So I'm going to write it down first. So I have here F. So we have here F prime, that is. I keep saying F. F equals to V plus minus VO over V minus plus VS, sorry. Right? And then for approach, which means we're going to take the upper signs, correct? So it becomes, let me switch to black, sorry. I know some of you may not like that. So here in this case, F prime is going to be F V plus VO over V minus VS, and then we plug it in. So we have, F is 400, and then 345 speed of sound plus 24.6 divided by 345 minus 33.5. Where did I get those numbers? Well, I got them from, converting to basically VO, which is 55 miles an hour. You can go ahead and convert for 24.6 meter per second, and V of the source, 75 miles an hour, is equal to 33.5 meter per second. Okay, there we go. You need to convert those. And when we calculate all of this, you'll end up with 475 hertz. So it is what? It's louder, excuse me, higher pitch, higher frequency. Okay. Now the last part is part B. As it moves away, same formula, except we take the lower signs. That's going to be V minus VO over V plus V sub S. We plug in all those numbers, I'm sure you know how to do that. And we end up with 339 hertz, lower pitch, lower frequency. Okay? And I think this is it for, let me just make sure. That's all I wanted to talk about today. And that's it. Have a great week. And let me know if you have any questions. Bye-bye.